today, we're plunging into a vision that has, well, captivated humanity for generations, sending humans to Mars.
It's a huge goal, isn't it?
Totally audacious, maybe closer than you think. But this deep dive isn't just about how we plan to, get there.
Right.
It's crucially about how we'll stay there.
That's the real challenge.
So we're going to explore NASA's detailed plans for human Mars missions.
Yeah.
And then really pivot to the groundbreaking stuff in space manufacturing and extraterrestrial construction, things that actually make a long-term presence seem,
well,
real.
Yeah, moving beyond just flags and footprints.
Exactly. To guide us through this incredible journey, we've lined up some fantastic sources.
Good stuff.
We've got NASA's Mars Design Reference Architecture 5.0, some in-depth reports on in-space manufacturing, extraterrestrial construction, and even a look into this, mind-bending concept of self-replicating machines from Carleton University.
Oh, that's fascinating territory.
Right, so our mission today is to unpack the current vision for Mars, highlight the amazing tech being developed, and sort of reveal how these efforts are shaping, humanity's multiplanetary future.
Sounds like a plan.
So let's start with the fundamental question.
Yeah.
Why Mars?
Yeah.
I mean, really. And why is building there beyond Earth so incredibly critical for these ambitious missions?
Well, it really boils down to a fundamental challenge of logistics and economics. It just does.
Okay.
For any long-duration mission beyond low Earth orbit, our current way of doing things, bringing every single nut and bolt from Earth, it simply won't cut it. Not for Mars.
Right.
I mean, think about the International Space Station right now.
Yeah.
We currently have around 13,000 kilograms of spare parts just floating up there on orbit.
13,000 kilos. Wow.
Yeah, and we send up about 3,000 kilograms more every year. That's the up mass just for maintenance.
Okay, seems like a lot.
It is. But here's the truly eye-opening part. Roughly 95% of those corrective spares, the ones meant to fix things that break, they were never actually used.
95%. Seriously.
Seriously. We send them because we just can't predict exactly what will fail, right?
So it's pure just in case.
Exactly. And that strategy is completely unsustainable for deep space missions, where resupply isn't just difficult.
It's basically impossible.
It's virtually non-existent.
Yeah. And the cost of just getting, say, building materials there must be, well, astronomical.
Oh, absolutely. Rockets, for all their power, are incredibly inefficient movers of heavy stuff like building materials.
Right.
Get this. Transporting just 1 kilogram of concrete mix to the moon costs us a staggering $1,200,000.
Wait, hang on. $1.2 million.
Yeah.
For 1 kilogram of concrete, like a bag you'd get at the hardware store.
Less than that, probably.
Yeah.
So imagine you wanted to, say, print a modest little structure, maybe 350 square feet.
Okay, like a small studio apartment size.
Yeah, something like the Chacon House Earth-based analog they talk about. If you wanted to print that on the moon, it would cost a mind-boggling $96 billion.
Billion. With a B.
With a B. And that's just for the dry concrete material, not the water, not the printer, not the labor, just the powder.
That's insane.
It really drives home the point, doesn't it? It immediately raises the question, how on Earth, or off Earth, I guess, do you establish a truly permanent, self-sufficient presence without completely breaking the bank?
Or needing constant, ruinously expensive resupply missions from Earth.
Exactly. It seems impossible without a whole new approach you have to build there.
Okay, the logistics problem is crystal clear. So how does NASA actually plan to tackle this? Their big master plan, the Mars Design Reference Architecture 5.0. It's from 2007, but it lays out a detailed vision, right?
It does, yeah.
What are its core goals for getting us there? And like you said, crucially for staying.
Well, DRA 5.0 outlines these key objectives that really evolve as our capabilities and our knowledge grow. So, goal I is the big one. Determining if life ever arose on Mars. And robotic missions, they're continuing to gather data for that right up through 2025.
Right, the rovers and orbiters.
Exactly. But the really ambitious part is goal 4 plus.
Plus side.
Yeah, that focuses specifically on preparing for a sustained human presence.
Oh. Okay.
This covers missions 4 through 10, basically developing all the knowledge, the capabilities, the infrastructure, everything needed for long-term living and working on Mars.
So moving beyond short sorties.
Precisely. And the scientific objectives are incredibly diverse. They really drive the whole mission design.
Like what?
Well, in geology, the aim is huge. Understanding Mars's whole evolution. how it went from potentially warm and wet in the Noachian period
Billions of years ago.
to its current cold and dry state in the Amazonian period. And the key insight there is that understanding this transition requires exploring really diverse locations.
So you can't just land in one spot.
Nope. You need extensive exploration, sample collection from vastly different geologic environments.
Which means you need serious mobility. Astronauts need to get around.
Bingo. Then there's geophysics. The goal there is characterizing the planet's internal structure, its composition, its dynamics.
Peeking inside Mars.
Yeah. And that means both huge planetary scale studies, like over thousands of kilometers, and more regional exploration geophysics.
What's it look for?
Things like the crust, the cryosphere, icy bits, potential water systems, the upper mantle.
How do you do that?
You need a whole suite of tools. Global seismic studies, magnetic surveys, active electromagnetic sounding to look for aquifers.
Water underground.
Right, reflection seismology, gravity measurements, ground-penetrating radar, even neutron spectroscopy for subsurface stuff.
Wow, okay. A lot of techniques.
It is, and the ultimate takeaway. Achieving these detailed science goals absolutely requires multiple, widely separated landing sites.
And that mobility again.
And the ability for humans to move significantly across the surface, yeah.
What else?
Atmosphere and climate studies are also critical, not just for pure science, but for keeping humans safe and operational, right?
Makes sense. Need to know the weather.
And interpret the life and geology findings. Plus, there's some cool ancillary science potential.
Oh, yeah?
Like using Mars as a platform for laser ranging experiments in astrophysics.
Going what?
Potentially testing alternative theories of gravity,
Yeah.
using the whole planet as an observatory.
Okay, that's pretty mind-bending. So
Yeah.
with those grand scientific and exploratory goals set, how does the mission actually get us there? What are the logistics of the journey itself? It sounds monumental.
It is monumental. The journey itself is broken into several phases, and each phase demands enormous capabilities.
How enormous.
Human Mars missions are incredibly mass-intensive. We're talking 800 to 1,200 metric tons for each mission.
Wait, 1,200 tons. How does that compare to, say, the ISS?
The entire International Space Station is about 400 metric tons.
Whoa. So like 2 to 3 times the mass of the ISS per mission?
Exactly, which means you need numerous heavy lift launches, probably using a vehicle like the Ares V concept they had.
Yeah.
Current estimates suggest at least 7 cargo launches just for one mission.
7 heavy launches before the crew even goes.
Oh, yeah. These launch campaigns actually have to kick off months before the optimal Mars departure window even opens.
Wow.
Oh,
Okay.
yeah.
What about assembly? Do they build this giant ship in orbit?
Well, the strategy for on-orbit ops is actually to simplify things as much as possible. Avoid complex construction.
Ow.
Systems are designed as discrete packages. They plan to use automated rendezvous and docking AR&D in low Earth orbit.
So robots put the pieces together.
Basically, yeah. Then the cargo elements just kind of loiter in Earth orbit for several months before they depart for Mars.
Waiting for the right alignment.
Precisely. The mission then unfolds in distinct phases. Phase 1 is cargo deployment.
Okay.
This sees the descent-ascent vehicle, the DAV.
That's the rocket to get back off Mars.
Yep. And the surface habitat, the SHAB, they're launched first.
The house and the ride home.
Pretty much. They get assembled in LEO, checked out thoroughly, and then injected into a minimum energy transfer trajectory to Mars.
The slow, fuel-efficient route.
Right. And this is about 2 years before the crew even leaves Earth.
2 years.
Yep. The trip alone for the cargo takes around 350 days.
Wow.
After that long cruise, they get captured into a highly elliptical Mars orbit, waiting.
Okay, so the house is waiting in orbit. Then what?
Then phase 2, crew deployment. This happens during the very next injection opportunity, roughly 2 years later.
Right.
The Mars Transfer Vehicle, the MTV, the cruise ride is launched, assembled, checked out in a LEO.
Okay.
They might even involve a separate checkout crew just for the MTV.
Making sure the taxi is ready.
Exactly. Then the actual flight crew departs Earth on a fast transit trajectory.
Faster than the cargo.
Oh, yeah. Much faster. Maybe 175 to 225 days, trying to minimize crew exposure time.
Makes sense. Radiation 0G.
All that. Upon arrival at Mars, the crew rendezvous with that pre-deployed SHAB waiting in Mars orbit.
Ah, they meet up with their house.
And the SHAB then serves as their transportation down to the surface. It's their lander, too.
Clever. Okay, so they've made it. They're on Mars. What's the day-to-day look like for these explorers? How do they live, move around, actually do the science?
Right. So DRA 5.0 outlines what they call a commuter surface mission scenario.
Commuter. Sounds kind of mundane for Mars.
Huh. Well, the core infrastructure is this centrally located monolithic habitat, one big base.
Okay.
Power is a big one. It would be supplied by a nuclear power plant.
Nuclear. Makes sense for continuous power.
Absolutely. And that nuclear plant is also absolutely critical for producing ascent propellant.
Fuel to get home.
And consumables like water, oxygen, buffer gases directly from Martian resources.
Living off the land. ISRU.
Exactly. This is where in situ resource utilization truly begins.
Okay, so they have power and a base. How do they get around the commuting part?
Right. This architecture includes 2 small pressurized rovers, think like Martian RVs basically, for 2 crew members each.
Pressurized, so they don't need suits inside.
Correct. Plus 2 unpressurized rovers, more like Apollo's lunar roving vehicle, for quick trips in suits. Okay?
And 2 robotic rovers as well, for support and scouting.
What about the range on those pressurized rovers?
Pretty modest, actually. About 100-kilometer total range before needing resupply from the hab. They could last maybe 1 to 2 weeks out on their own.
So short camping trips?
Sort of, yeah. Minimal onboard habitation. But they're designed to be nimble, get close to interesting cliffs or canyons.
Right. And the exploration strategy itself, how does that work with this setup?
It relies heavily on traverses, trips away from the base.
Okay.
See, landing sites are often chosen for safety, right? Flat, boring terrain, basically.
Easier to land.
Exactly. But that often means they're far from the most scientifically juicy areas, like the edges of a Cetus planitia or Cetus major they mentioned.
You have to travel.
You have to travel. This makes the rovers absolutely essential. Because a human's walking range in an EVA suit is, pretty limited, maybe 20 kilometers total sortie distance, max.
Gotcha.
The habitat itself would have space inside for onboard science experiments. A lab, analyzing samples right there.
Yep. And the rovers carry the essential field equipment. Core samples drilled out on traverses would be brought back to the habitats lab for detailed analysis.
You mentioned drilling. How deep can they go?
Subsurface access is seen as crucial. So a drilling capability, probably moved around by the unpressurized or robotic rovers, is needed.
Why drilling?
To reach depths of tens, maybe even hundreds of meters. That's where you'd search for subsurface water or ice, look for layered rock records, stratigraphy, or even evidence of past or present life hiding underground.
Okay. A Martian oil rig, sort of.
Sort of. These drilling ops would likely be largely automated, but with human supervision close by.
Right. And this brings us back to that ISRU thing,
Yeah.
living off the land. How critical is that?
Oh, it's absolutely fundamentally critical for any kind of self-sufficiency.
How does it work?
The ISRU plant basically takes Mars's atmosphere, which is mostly carbon dioxide, right?
CO2.
And it converts that CO2 into oxygen. For breathing, yes, but mainly for rocket propellant oxidizer.
Wow. Making rocket fuel out of thin air.
Pretty much. Using something called solid oxide CO2 electrolyzers, or SOCEs, high-tech CO2 splitters.
Okay.
It also generates water and buffer gases like nitrogen and argon for the habitat atmosphere.
Where does the water come from?
Well, methane fuel for the ascent vehicle is actually brought from Earth in this plan.
Okay.
But hydrogen, maybe also from Earth or potentially extracted locally later, is reacted with the Mars-produced oxygen to make water using chemistry, like the Sabatier reaction.
Ah, okay. Making H2O.
Yep. And nitrogen and argon are also separated from the thin Martian atmosphere for breathing gas mix.
And the nuclear reactor powers all this.
Nuclear fission power is basically seen as necessary for the continuous propellant production needed to get the crew home. It's a huge energy demand.
Man, this whole endeavor sounds incredibly challenging. So many complex pieces needing to fall into place perfectly. What did NASA see as the biggest hurdles, the major roadblocks to making this happen?
Yeah, the challenges they identified are definitely multidisciplinary, and they truly demand significant breakthroughs. It's not just refining existing tech.
Like what? Number one.
First, human health and performance. It's a huge one.
The astronauts themselves.
Exactly. Long-duration deep space missions expose crews to serious radiation, galactic cosmic rays, solar particle events, and also the effects of reduced gravity, like on Mars or in transit.
Yeah.
Protective measures are absolutely critical. Shielding, medical treatments, it requires extensive medical research and countermeasures. A lot of that work gets tested on the ISS and in ground labs.
And if we don't solve those health issues...
Without major advances there, mission durations might have to be severely limited, which could potentially make the whole venture impractical, or at least much less effective scientifically.
Okay, health is huge. What else?
Another massive hurdle is landing large payloads on Mars. Really massive.
We talked about the 1,200 tons getting to Mars orbit, but then you have to land parts of it.
Precisely. And Mars's atmosphere is only about 1% as dense as Earth's.
Super thin.
Which makes it extremely difficult to use parachutes or atmospheric drag to slow down heavy spacecraft.
Right, not much air to push against.
Exactly. Our current robotic lander capabilities, like Curiosity or Perseverance, they max out around 1 metric ton landed.
1 ton.
Human-rated systems, though, the Habitat, the ascent vehicle, they need to land maybe 40 metric tons of useful payload each.
40 tons, from 1 ton to 40.
It's a gigantic leap. It requires fundamental research in hypersonic aerodynamics, new materials science, advanced propulsion for braking. It's like going from, I don't know, dropping a pebble gently to placing a small building down without breaking it.
Okay, that's a serious challenge. What's next?
Then there's the sheer need for heavy lift launch capability from Earth.
Back to the rockets.
Yep. Even with squeezing every bit of efficiency out, these human Mars missions require that total mass of 800 to 1,200 metric tons sent from Earth. So a heavy lift launch vehicle like the ARISV concept or something similar like Starship is absolutely essential just to minimize the number of launches needed.
And the complexity of all that orbital assembly.
Exactly. It's key to making the mission architecture even remotely feasible, economically and logistically. Heavy lift? Anything else major?
Advanced propulsion for the journey itself.
Faster engines.
Essentially, yeah.
Yeah.
While current chemical propulsion, like we use now, could theoretically work, it means long trip times.
Right, that 175, 225-day fast track, or even longer.
Nuclear propulsion, either nuclear thermal or nuclear electric, is a really compelling prospect.
Why?
It could tremendously reduce either the total mass you need to launch from Earth or, maybe more importantly, drastically cut the travel time.
Getting the crew there faster, less exposure.
Exactly. And alongside that, you also need breakthroughs in long-duration cryogenic fluid storage, keeping those propellants super cold for years.
Right, fuel can't boil off. Okay, one more.
And finally, maybe the most overarching one, reliability and supportability.
Things can't break.
Or if they do, you have to be able to fix them, with virtually no resupply capability from Earth once you're out there.
Yeah.
Mars missions demand extremely high reliability, like orders of magnitude better than what we might accept for LEO. And a totally self-sufficient supportability approach.
Crews have to have all the resources, tools, spares, and knowledge needed to sustain all critical systems, life support, power, rovers, for the entire mission duration. Years.
Wow.
And that requirement itself is a major mass and volume constraint, packing everything you might need.
The underlying problem really is, if something critical breaks, you can't just call Amazon Prime for a next-day delivery to Mars.
Exactly. You are on your own.
You know, it really hits home how critical these breakthroughs are, that inability to just call Earth for a spare part. If logistics from Earth are so constrained and reliability is absolutely paramount, this really underlines the importance of making things in space.
Right there. Absolutely. That's the fundamental shift in thinking, moving from shipping everything to making it on demand.
Yeah.
Remember that stat about the ISS spares? 95% of corrective spares never used.
Yeah, crazy.
Because you just can't predict what's going to break. That just-in-case strategy is completely unsustainable for missions beyond LEO. Resupply is simply not an option.
So in-space manufacturing, ISM, is the answer.
It aims to be, yeah. ISM offers a path towards more sustainable, more flexible missions. How? Through on-demand fabrication, replacement, and even recycling of parts and materials.
Making what you need when you need it.
Exactly. As one expert put it, ISM likely provides a blanket coverage against a broad set of uncertainties that you can't get anywhere else.
Covering the unknowns.
Right. Another expert went even further, basically declaring, we will build everything. Maybe a bit ambitious, but it shows the mindset shift.
Build everything. Wow.
And it also provides significant volume packaging savings. Think about it. Raw materials like spools of plastic filament or metal powder.
Yeah.
They can be stored much more densely than bulky prefabricated components. So you save on launch mass and volume.
That makes sense. Less wasted space. So how has this idea evolved? Where are we now?
Well, the evolution of ISM has been really fascinating to watch. Early concepts back around 2004 were part of something called the In Situ Fabrication and Repair, or ISFR program. It envisioned capabilities for basic fabrication, repair, even starting to think about constructing habitat structures.
Building shelters.
Yeah, things like radiation shielding, potentially using local resources, autonomous construction, plus non-destructive evaluation and recycling. The core ideas were there early on.
And more recently.
By around 2016-2017, NASA's portfolio had really expanded significantly. It included things like in-space polymers.
Like the 3D printer on the ISS.
Exactly, the on-demand 3D printing of tools and parts on station. Also, in-space recycling, demonstrated by the refabricator experiment, which turned waste plastic back into filament.
Cool. Closing the loop.
Yep. Multi-material Fab Lab concepts for integrated workstations, printed electronics, and developing the validation processes needed to trust these in-space products.
Using the ISS as a test bed.
Absolutely. The ISS is really the key test bed for maturing these technologies in the actual space environment. Microgravity, vacuum, radiation.
And where are things heading now?
Currently, efforts are continuing in several key areas. On-demand metals manufacturing is a big one, 3D printing metal parts, not just plastic.
More structural component.
Definitely. Also, more advanced recycling and reuse, like reprocessing packaging materials into feedstock for 3D printers, and ongoing work in on-demand electronics manufacturing.
Printing circuits.
Printing sensors, power devices, simple circuits. Yeah.
Is this just a NASA thing?
Not at all. It's becoming a global effort. The European Space Agency, ESA, just had their metal 3D printer technology demonstrator on the ISS successfully print its first test specimens back in May 2024.
Oh, wow. Very recent.
Yeah. And in South Korea, the Korea Institute of Civil Engineering and Building Technology, KICT, they've developed microwave technology.
Microwaves. For what?
To produce construction materials from simulated lunar regolith, lunar soil, creating what they call microwave bricks.
Bricks from moon dust using microwaves. That's wild.
It shows this global push towards using local resources and manufacturing off Earth.
Okay, so beyond just making spare parts or tools, the real game changer seems to be building the big stuff. Habitats, landing pads, infrastructure, using local materials on the moon or Mars.
Exactly, extraterrestrial construction.
How did this idea really gain serious traction? And what are the unique challenges of trying to build, a house on the moon?
Well, there's been a very clear confluence of events recently. Political will, public interest, and significant government investment have really propelled this forward.
What kind of moments?
You can point to catalyst moments like NASA launching its 3D printed Mars Habitat Centennial Challenge back in 2015.
Right, I remember that. Some wild designs.
Totally captured the public imagination. Then ESA Director General Jan Werner proposed the Moon Village vision in 2016, aiming for this open international collaboration on the moon.
Okay.
And perhaps most notably, here in the U.S., Vice President Pence in both 2017 and 2019 explicitly stated the policy goal: return astronauts to the moon not just to leave footprints again,
And to stay.
but to build the foundation we need to send Americans to Mars and beyond. That was a clear policy directive.
And that led to?
Directly to NASA's Lunar Surface Innovation Initiative, or LSII. Its specific goal is accelerating technologies needed for lunar surface exploration, explicitly including in-situ resource utilization and sustainable power. Construction is key.
So real programs and funding started flowing.
Yes. And ESA also launched its own big effort in 2019, the Discovery Campaign on Off-Earth Manufacturing and Construction.
What did that look at?
Exploring all the enabling technologies across different themes. How do you handle regolith? How do you process it? In-situ manufacturing, recycling, habitat design. A really broad look. It's a concerted international effort now.
Okay, but the challenges of building there must be immense. You're not just dealing with, bad weather?
Oh, the challenges of extraterrestrial environments are extreme. You have to design for and build in conditions that are, alien.
Like what?
Intense radiation, for one. Galactic cosmic rays, unpredictable solar particle events. You need serious shielding.
Right. Can't just build with drywall.
Definitely not. Then there are meteoroid impacts. Even tiny ones can be dangerous over time. So structures need robust shielding for that too.
Okay. Radiation impacts.
Extreme temperatures, huge swings between sun and shadow, and hard vacuum. Both cause significant stresses on materials.
Materials expanding and contracting.
Constantly. And then there's even seismic activity. Moonquakes are a real thing. So your foundations have to handle that. You're basically building in the harshest, most unforgiving environment imaginable.
Wow. So given those insane conditions, how do we even begin to test building techniques? Are we just sending robots up and kind of hoping for the best?
Not quite. What's really fascinating here is how robotics research being done for terrestrial construction is directly informing how we might build in space.
Earth-based construction robots helping space exploration. How?
Yeah, the National Renewable Energy Laboratory, NREL, did this pilot study on robotic assembly of wall systems for regular buildings here on Earth. And the findings are highly relevant. They used a standard 6-axis robotic arm, like you see in factories, with different tools on the end grippers, drills,
Right.
to build a prototype wall section. Wood studs, insulation, sheathing, pretty standard stuff.
What did they learn that applies to Mars?
They found significant, sometimes frustrating discrepancies between their computer simulations and what actually happened when the robot tried to assemble the physical parts.
The virtual model didn't match reality.
Exactly. For instance, parts that fit together perfectly in the CAD simulation didn't quite align in reality. Why? Subtle tolerance errors in manufacturing, friction the simulation didn't account for.
Ah.
Weight distribution also caused unexpected problems. The robot might sag slightly under load, causing misalignment. Sometimes they had to physically modify things, add counterweights, shave down a bit of material.
Tweaking things on the fly.
Yeah, even the porosity of materials like plywood or foam insulation messed with the vacuum suction grippers the robot used.
Air leaking through the material.
Right. They had to do things like put tape on the surface just to get an airtight seal for the robot to grab it properly.
So even with the most perfect simulations, you couldn't fully account for the messy reality of actually putting things together. That seems like a critical insight.
It really is. Especially for off-world construction where a mistake isn't just costly, it could be catastrophic.
Absolutely.
The profound lesson from this Earth-based study is that actual physical testing and having robots that can adapt are absolutely indispensable for building off-world.
You can't just rely on the digital plan.
No. The success of construction robotics depends heavily on really good design for manufacturing and assembly DFMA strategies, thinking about how the robot will build it from the start,
Okay.
and needing extreme precision in manufacturing the components themselves, probably using things like computer numerical control, CNC, milling.
Super precise parts.
Yep. Virtual simulations need to get much better, too. They need to evolve to include multi-physics behaviors, friction, gravity effects, material properties, not just the robot's arm movements, the inverse kinematics.
More realistic physics in the simulation.
Right. And the future of robotic construction, both here and off-world, will likely involve multimodal feedback sensors.
Like,
Vision, obviously, but also haptic feedback touch, maybe acoustic sensors listening for problems. Using machine learning so the robot can autonomously correct its course when things don't go exactly to plan.
robots that can improvise a bit?
Exactly. And also, telerobotic operation through digital twins,
What's that?
creating a highly accurate virtual replica of the remote construction site and robot. This allows Earth-based operators to control the distant robots with much higher precision and situational awareness.
Like a super realistic video game controller for a Mars bulldozer.
Kind of, yeah.
Okay, this all sounds incredibly complex, but we're still largely talking about bringing specialized machines, maybe some materials, from Earth to get these off-world bases started. What's the ultimate long-term vision for truly independent, self-sustaining off-world civilizations? Does it go beyond just ISRU and construction?
It does when you step back and look at the really big picture, the really long-term vision. The conversation eventually leads to self-replicating machines.
Self-replicating.
Yeah.
Like robots building copies of themselves.
Exactly. Some experts argue that this is the only robust approach to truly spreading human presence throughout the solar system on a large scale.
Why the only way?
Because the core idea is simple but incredibly powerful. Self-replication offers exponential growth in productive capacity.
Exponential growth. How does that work? Can you give us an example?
Sure. Imagine launching just one single, maybe 10-ton, self-replicating factory unit to the moon. Let's say it's designed to build copies of itself.
Okay, one seed factory.
Right. And let's say each factory takes about 6 months to mine resources and build 2 new offspring factories. So it doubles roughly every 6 months.
Okay, seems slow at first. 1 becomes 2, then 4.
It seems slow initially, yes. But because it's exponential, in just 6.5 years, that's only 13 generations of replication. You wouldn't have 2 or 4 or 8 factories. You'd have over 1.5 million factories operating on the moon.
1.5 million from one
Yeah.
in less than 7 years.
Exponential growth. And think what that does to the cost. If that initial 10-ton factory costs, say, $7.5 billion to launch, That's $750,000 per kilogram of productive capacity.
Still expensive.
But after 6.5 years, you have millions of tons of factory capacity built in situ. The specific cost per kilogram of that productive capacity drops dramatically to less than 50 cents per kilogram.
50 cents. Down from almost $1 million.
Because you effectively sidestep those astronomical launch costs for the vast majority of the industrial base. You only launch the seed. It's a total game changer for scaling up off-world industry.
Okay, my mind is kind of blown. What's the theory behind this? Can machines really build themselves?
Well, the theoretical foundation goes back to the brilliant mathematician John von Neumann. He conceived of the universal constructor.
Universal constructor.
Yeah. A theoretical machine capable of manufacturing any other machine, including, crucially, a copy of itself, given the right instructions and raw materials.
Okay, so it's theoretically possible. How do you adapt that for space?
For the unstructured environments of space, dusty surfaces, varying resources, the concept is adapted. You wouldn't have one single giant machine, probably. Instead, you'd have a suite of specialized kinematic machines.
Kinematic meaning?
Machines that move, basically. Things like mining robots for digging up regolith, programmable pumps for chemical processing of those raw materials,
Okay.
mills, lathes, and especially 3D printers for autonomous manufacturing of parts, and robotic manipulators for assembly, putting the parts together.
A whole ecosystem of robots.
Exactly. And what's fascinating is the argument that all these different machines are fundamentally built from just a few core components: electric motors, actuators, sensors, and control systems. If you can make those self-sufficiently,
You can make anything else.
you're well on your way. Yeah.
But for true self-replication, surely there are conditions. You can't just magically make stuff out of nothing.
Absolutely. There are 3 critical closure conditions that must be met. It's all about proving you can truly live off the land.
Okay, what are they?
First is material and parts closure. This is a big one. Every single component needed to build the next generation of machines
Yeah.
must be manufacturable from a restricted, predefined inventory of raw materials found in situ right there on the moon or Mars, sometimes called a demand-ite list.
So you had to work with what's available locally.
Exactly. And using only a limited set of manufacturing processes and machines that are themselves part of the replicable set.
What kind of materials are we talking about? Iron, aluminum.
Things like iron, aluminum, silicon for electronics and glass, maybe magnesium, titanium. Basic metals and ceramics you can get from common minerals. The moon's geology, for instance, is relatively simple. Lots of pyroxene, plagioclase, olivine, ilmenite. These contain those key elements.
Well, the raw ingredients are there.
Mostly. Some specialized elements or chemical reagents, like maybe sodium chloride for certain processes, might initially need to be imported from Earth as vitamins, but the goal is absolute minimization of that. You need closure.
Okay, material closure. What's second?
Second is energy closure. This seems obvious, but it's crucial. The energy generated by the system must consistently exceed the energy consumed by mining, processing, manufacturing, and replicating.
The system has to power itself and grow.
Right. This means maximizing the use of direct environmental energy. Solar thermal using lenses or mirrors is a big one, and achieving very high energy conversion efficiency.
Making the most of the sunlight.
Yeah, technologies like photon-enhanced thermionic emission, PEAT, are mentioned, with potential efficiencies of 30–50%. Basically, you're building your own self-expanding power grid alongside the factories.
Okay. Materials, energy. What's the third closure?
Third is information closure. This is a bit more abstract. The total amount of information needed to specify how to build and operate a machine.
The blueprints, essentially.
The blueprints, the software, everything must not exceed the system's capacity to store, transmit, and process that information using the computers it can itself replicate.
So you can't need a supercomputer design if you can only build simple processors.
Exactly. It encourages simpler designs, modularity, and maximum reuse of parts and software modules. Keep the information manageable.
Wow. Material, energy, information closure. It's a high bar. So how do you meet these constraints? What kind of technologies are actually practical for this? Are they super futuristic or?
That's a great question. The approach discussed is often focused on surprisingly robust manufacturable technologies, sometimes even referred to as Iron Age or even steampunk technologies adapted for space.
Steampunk? Like brass goggles and vacuum tubes.
Well, maybe not the goggles, but potentially the vacuum tubes, yes. The idea is using tech that's easier to make from raw materials, more tolerant of the environment, even if it's not the absolute cutting edge we use on Earth today.
Okay, tell me more. Metals first.
For metals, a key process is hydrogen reduction of ilmenite. That's an iron titanium oxide mineral found readily on the moon.
Okay.
Heat it with hydrogen around 1,000 degrees Celsius, and you get out water, which you recycle metallic iron and titanium dioxide.
So you get iron directly.
Yep. And this iron can then be refined using basic metallurgy into various useful forms. Wrought iron, cast iron, different types of steel like tool steel or silicon steel for electric motors, even alloys like Kovar or permalloy for magnetic shielding.
What about other metal? Nickel, cobalt.
Those might be sourced from processing meteoritic material found mixed in the regolith. The moon gets bombarded constantly.
Okay, so basic metals seem feasible. What about plastics? Ceramics? Things for insulation.
Fused silica glass is a good candidate for electrical insulation or optical fibers. You can make that from minerals like anorthite, common on the moon.
Okay, glass from rock.
For plastics, the focus might be on silicones. They're quite resistant to UV radiation and temperature extremes. And you can potentially make them from syngas derived from metal oxides and minimal carbon, maybe brought initially or found in carbonaceous chondrites. Minimizing reliance on Earth-sourced carbon is key.
Right. What about electronics? Sensors? Cameras?
Photosensitive materials like selenium are mentioned. Selenium is essential for imaging sensors, like in cameras or photocopiers. It can potentially be extracted from lunar regolith or meteoritic sources in small quantities.
Okay. And how do you actually make parts from these materials?
A generalized 3D printing suite is envisioned, not just plastic printers. Things like selective solar sintering.
Using sunlight to print.
Yeah, using large Fresnel lenses or mirrors to focus sunlight intensely, generating maybe 1,500 degrees Celsius spot temperatures, hot enough to melt and fuse regolith or metal powders directly.
Wow, printing with focused sunlight.
And also electron beam additive manufacturing, EBAM, using an electron beam in vacuum to melt metal powders or wire feedstock very precisely. These kinds of additive manufacturing techniques could potentially even print passive electronic components like resistors or capacitors directly onto substrates.
Okay, but what about active electronics? Computers? Control systems? You mentioned vacuum tubes.
Yeah.
Seriously?
Seriously, this is the steampunk electronics idea.
Yeah.
Using vacuum tubes, thermionic valves instead of modern solid-state transistors.
Why on earth go back to vacuum tubes? They're huge and inefficient.
They are bulky compared to microchips, yes, but they have some key advantages for this specific context, such as they are generally much simpler in construction using basic metals and glass. They are potentially printable using additive manufacturing techniques, and crucially, they are inherently much more tolerant to radiation than delicate solid-state electronics.
Ah, the radiation angle. That makes sense for space.
Right. Now, you wouldn't build a complex CPU like the one in your phone using vacuum tubes. It would be the size of a building.
Yeah.
But you could potentially form distributed control architectures, maybe using analog neural networks, which are surprisingly powerful, they're Turing complete, and scale better for certain tasks. Simpler, more robust, locally manufacturable control.
Distributed radiation-hardened brains. That's clever. Are there specific components they think could be fully self-replicated?
Yes, there are some key examples. Full 3D printed electric motors are a target. Printing everything.
What?
The rotor, the stator, the copper wiring, the shaft, even simple bearings, all from locally sourced materials.
A whole motor printed.
Yeah. Another key example is the magnetron.
Like in a microwave oven.
Exactly like in a microwave oven. It's essentially a macroscopic vacuum tube, but it has elements similar to an electric motor inside. It's seen as critical for generating microwaves needed for beaming power from solar power satellites or even for processing regolith directly, and it's potentially printable.
Wow, okay. What about power generation and storage itself?
Electric power conversion could use those thermionic devices, essentially vacuum tubes working in reverse, or the more efficient photon-enhanced thermionic emission, converting heat or light directly to electricity.
And storing that power. Batteries.
Batteries are tricky chemically. Flywheel energy storage is often proposed.
Spinning disks?
Yep. Electromechanical batteries, they can offer high energy density, maybe 100 kilojoules per kilogram using glass composites, and crucially, they can be made largely from locally sourced metals, glass, and magnetic materials. No complex lithium chemistry needed.
Mechanical batteries made from moon rock.
And even propulsion gets a rethink. Electromagnetic launchers, coil guns, or rail guns are explored.
So launch things.
Yeah, to launch payloads, maybe process materials off the moon using only solar-derived electrical energy. This avoids consuming potentially scarce or non-renewable propellants like water ice if you want to build a truly sustainable closed-loop system.
It's a completely different way of thinking about space industry, building an entire industrial ecosystem from scratch, designed to replicate itself using local resources.
That's the ultimate vision.
This future of self-sufficient off-world outposts, powered by self-replicating machines, it's incredibly exciting. Almost feels like science fiction becoming real. But let's bring it back down to Earth, or maybe low Earth orbit for now. What's realistically standing in the way of making just the initial steps, the in-space manufacturing and construction capabilities, a widespread reality sooner?
Right. Moving from concepts and experiments to routine operations, there are definitely hurdles. The analysis points to about 4 key challenges that need systematic addressing.
Okay, what's the first one?
First, we need more compelling use cases. Real ground truth.
Meaning?
We need clear, hard-nosed analytical evidence showing exactly where and when in-situ manufacturing or repair or recycling isn't just a neat idea, but becomes absolutely inevitable, or provides undeniable benefits.
It's like proving it really simplifies logistics or cuts costs drastically or enables missions that are otherwise impossible.
Exactly. The theoretical benefits are often clear, but demonstrating the practical, mission-critical need needs to be rock solid to drive investment and adoption.
Okay, prove it's essential. What's second?
Second is certification. This is a really major hurdle.
How do you guarantee a part made in space is safe and reliable?
Precisely. How do you qualify and certify hardware that's manufactured in space or on the moon or Mars when you don't have the decades of experience, the ground infrastructure, the established processes you have on Earth?
Yeah, you can't just send every printed part back to an Earth lab for testing.
Right. While NASA does have standards, like NASA Standard 6030 for additive manufacturing processes, figuring out how to actually certify the part made in space for critical applications, that needs much more development. It's a completely new regulatory and engineering frontier.
Trusting the process, essentially. Okay, that's big. Third challenge.
Third is dealing with mission timelines.
Things take a long time in space development.
They do. New technologies typically require a decade, often much more, to go from concept to being fully baseline incorporated into a major space mission plan. There's a lot of risk aversion, understandably.
Right.
Now, the rapid adoption we saw for additive manufacturing in terrestrial applications, like printing rocket engine components.
Yeah, companies are doing that now.
That was driven by very clear business cases, faster, cheaper production, and strong government leadership pushing it. That same clear, urgent scenario, unfortunately, does not hold for in space manufacturing, according to the sources.
Why not?
The immediate return on investment isn't always as obvious. The applications are more niche initially, and the experience base is still being built. It takes longer to get adopted into those long mission planning cycles.
Okay, slow adoption. And the last challenge, number 4.
And finally, there's the demand signal, especially for private industry.
Companies need to know there's a customer.
Exactly. Private companies need a consistent, reliable, and frankly strong government demand signal to justify making the significant long-term investments needed to develop these capabilities and to mitigate the inherent risks involved in space tech.
Makes sense. They won't build it if no one will buy it.
Right. And unfortunately, the sources note that sometimes in-space manufacturing and lunar surface construction technologies have received relatively low rankings in things like NASA's civil space shortfall assessments.
Which doesn't exactly scream, we need this now.
No, it doesn't send a strong positive signal to potential investors or companies, making it harder for the private sector to fully jump in and accelerate development.
So compelling use cases, certification, long timelines, and a clear demand signal. Those are the big hurdles.
That seems to be the consensus, yeah. The grand challenge, as one source puts it, is really to integrate all these elements, to prove out the entire process from design to in-space production to certification to operational use and show it's ready for mission-critical applications.
How do we do that?
It absolutely requires sustained government support, likely through cross-agency collaboration, maybe NASA working with DARPA, for instance.
Right.
To establish those clear rationales and use cases, to standardize requirements where possible, and critically, to fund and fly comprehensive technology demonstration missions.
Flight tests to prove it works.
Exactly. Set an example, build flight heritage, reduce the risk, and pave the way for future initiatives, both government and commercial. It's about bridging that gap from promising concept to operational reality.
Wow, what a deep dive this has been. We've gone from the intricate plans of NASA's Mars Design Reference Architecture 5.0, detailing everything from the science goals and mission logistics to what daily life might actually look like on the red planet.
Get the commuter concept.
Right. Then through the pioneering efforts in in-space manufacturing, printing parts, recycling materials,
Building what you need where you need it.
all the way to that audacious long-term vision of self-replicating machines, building an industrial base across the solar system.
It's quite a spectrum of possibility.
It really makes it clear that humanity's future in space isn't just about, getting there anymore. It's about truly living and thriving independently off Earth.
Indeed. The ambition is just immense, isn't it? But the scientific and engineering ingenuity being applied to solve these colossal challenges is equally impressive. We really are moving from that old paradigm of basically bringing Earth with us in a tin can to a new one of actually making ourselves at home among the stars, using the resources we find there. The implications of actually achieving that are just profound.
Absolutely. It makes you think, imagine a future, maybe not even that distant, where Martian habitats aren't painstakingly assembled from Earth-sent modules, but are autonomously constructed, maybe even 3D printed, by robotic systems using the very dust beneath their feet.
Crafted from Mars itself.
Yeah. What kind of societal shifts might occur when or if our civilization truly expands exponentially, fueled by self-replicating industry beyond Earth? What does it mean when humanity is effectively unshackled from the gravitational well and the resource limits of our home planet?